Hi, thanks for having me to present my work here. Today I'll be talking about pure states and eigenstates, eigenstate thermalization in Schwarzian theory. And this is some work I've done in collaboration with Julian and Manuel, and based on some preprints that appeared earlier this year on arXiv. Uh, uh, Hi. So, uh, yeah, there's a big gap here because I'm currently not affiliated to any place, so I didn't want to put in anything there. But I realized that the poster says I'm affiliated to Geneva, so and that's how it's gonna be, I guess.
Even for 1 month?
Yes, 1.5 to be more precise.
1.5.
Yeah. So the plan of my talk is that I will start with describing how Schwarzian theory can be derived starting from a two-dimensional Liouville theory and doing a dimensional reduction. And I will discuss how imposing different boundary conditions on the Liouville theory on an open string corresponds to some pure states in the one-dimensional Schwarzian theory, and these different states corresponds to different coadjoint orbits of the Virasoro group. Uh, from there, I will move on to discuss the extended eigenstate thermalization hypothesis, and then which basically the statement of the extended eigenstate thermalization hypothesis is that it extends the eigenstate thermalization for a more general class of operators, saying that the expectation value of those operators in a pure state, in a generic pure state or in an energy eigenstate, also is approximately thermal expectation values under certain approximations. From there on, I will move on to discuss some exact and semi-classical computations of correlation functions in the pure states that I'll derive in the earlier part of my talk, and then finally I'll conclude my talk. So, before I dive into the details of my work, let me just present the big picture. Why am I doing this? So, the idea is that the motivation behind our work is rather elementary. We just want to understand how is it that certain how is it that quantum mechanical systems thermalize in the classical limit, and we also want to use our understanding of this question to answer the question of black hole formation and eventual information loss or lack of information loss in a theory of quantum gravity. Okay, and we aim to do that.
It's not a classical question.
Yes, yes. And the reason we are using Schwarzian theory is like it's a simple one dimensional, it's an example of a simple one dimensional theory where we can do a lot of exact calculations. So we just hope that we'll be able to learn a lot more by doing exact calculations in this theory.
So Pranjal, maybe you're going to say more, but when you say that you obtain thermal physics in the classical limit, you mean that you want to understand thermalization and loss of memory of the initial pure state as a consequence of large n?
Yes, it could be large n, it could be h bar going to 0, but yes, some kind of classical limit that. In this case, it will be large n, or n would be sitting silently, there will be some other parameter in this case, but there is a parameter which goes to, which becomes large, characterizing the classical limit.
So when you talk about ETH, there also you would say that it's a states with energy comparable to n square or something. The ETH should be valid for
Those states.
for those states.
Yes, yes.
Just curious what your, I should really wait, of course. But what is your view then about the Schwarzian theory? Is it, in your view, a quantum mechanically complete unitary theory, or is it, in your view, the analog of membrane dynamics for a near extreme system?
It's an analog of a membrane dynamics. So it's a low energy theory, but
so it may not help vis-a-vis the unitarity question per se. I mean, it may help vis-a-vis how thermalization and so
yes,
on. But
Yes, yes. But uh, means some interesting observations that we made during this work also, because it gets related to the 2D Liouville theory, and that is a UV complete theory in some sense, and it's a dimensional reduction. I mean, there is still something more to it than just obtaining just the thermalization part of it. Like the Schwarzian theory as a standalone theory can possibly get something more than like without even knowing the UV completeness of the where it comes from. So I'm not sure to what extent in this particular case we can push without knowing the UV completeness of the theory.
It's very interesting. But I think Sandeep's question is that if it is a sector of a certain theory, then you can't push for unitarity because stuff can go into
Right. That's yeah.
other sectors.
Yes, that's right. Yeah.
But what is the problem with that theory, the standalone theory? How do you see the unitary violation?
Right. I don't know. I mean, I think it's not quite a settled question, at least in my
Yeah.
mind. But the general, I would expect that it's not a complete quantum mechanical theory. Of course, you should say, but I'll give you one small piece of evidence for this. To the extent it arises in the low energy limit of near extremal black holes, the most striking quantum mechanical property about the near extremal black holes is the ground state entropy. And you expect any unitary theory to capture the ground state entropy and then tell us, in the context of having so many ground states, how does the information come out? And the Schwarzian theory certainly does not provide a microscopic explanation for the ground state Bekenstein-Hawking entropy. So therefore, I would be skeptical that it would provide a unitary complete theory. But you should say more. And just to pose a question, because if you're here for a little while more over the days, we can talk. I mean, I think this is a good question also to learn from others who are experts in CFT. The most crystal clear example in my mind to think about this is if you have ADS3, an extreme BTZ black hole in ADS3, which gives rise to a near horizon ADS2, which is described by Schwarzian. Then the question is, in a precise way, what sector of the CFT2 dual to ADS3 is being captured by the Schwarzian theory? And is that a complete sector in its own right? I think if we were to understand this very precisely, my feeling is we would see no, it's not. But I think that's the kind of question which would be helpful. And I think maybe your work will allow us. Sorry to talk so much.
Actually, but it's also related to this remark in the Stanford Witten paper, which says that the density of states that apparently the density of states that you get from the Schwarzian theory cannot be interpreted as the density of states of Hamiltonian theory.
That's true.
Because if it did have a continuum density of states, then your partition function should not be finite. But it's actually finite. If you compute the path integral is finite, so they are saying that path integral cannot be interpreted as trace of e to the power minus delta h.
Good point. Very good point. But it would be nice to understand better to what extent, I think that's perhaps your angle.
Yes.
To what extent it captures.
Yes.
And so I think if you can make it precise, it's a very useful.
Also, he will tell us that it actually is related to there's some two-dimensional UV complete theory. So yeah.
Right.
Sorry,
No.
I shouldn't let the cat out of the bag.
There is a paper by Harding who tries to get Schwarzian 2D CFT. So at finite temperature, some part of the global diffeomorphism gets broken because of the temperature. From there, he tries to argue that you can get Schwarzian in 2D CFT entirely.
2D itself. And so this is the kind of thing which we should understand in the context of ADS3. How do you get a Schwarzian?
Yes, yes.
Okay, I didn't know. We should discuss this more. I think
He's going to tell us.
you'll tell
No.
us when you.
I don't think I'm talking about what that particular thing, but yeah. Okay.
Sorry.
Yeah.
Because with TIFR.
No, that's
Speaker
the
barely gets a chance to talk. Sorry.
that's the fun part of being in TFR, because then I don't even have to worry about completing the talk in an hour. Because yeah, I've had some bad experiences with that. So yeah. Uh, so yeah, and let me also just summarize because my talk is it contains a bit of detail. So in case you get lost in all the details, let me just put in the punchline of what we find in our work. So we analyze various class of states in the one-dimensional Schwarzian theory, which are all pure states. And all these states are related to different Virasoro orbits. And whether or not they show thermalization depends on which particular orbit they lie on. Okay, so the uh, basically the class of the kind of states that I'll be considering are what I call as the pure energy eigenstates of the Schwarzian theory, certain coherent states of the Schwarzian theory which can be created by starting with an energy eigenstate and inserting kind of a vertex operator. So it's, I'm not being extremely precise, but you take this state, insert a vertex operators which lifts it from lying on a parabolic orbit to one of the different orbits. So in these states, depending on this parameter r, which decides whether you are on a elliptic orbit or hyperbolic orbit, you get thermalization or you don't get thermalization. And the last class of states that I'll be discussing is the ones created by some operator insertions in the theory on vacuum. And I find that such operator insertions creates states which are parabolic, but they only thermalize weakly. In the sense, these operators insertions of like these states, if you if you have if you have a background temperature and you insert an operator like this, then the temperature perceived by some light operators or some probe operators will see an increased temperature. But if I take the background temperature itself to 0, then the probe operators don't see any temperature. So that's what we call a weak form of eigenstate thermalization, because it's like you need a background temperature to see thermalization by itself, like the effect of these heavy operators. So
In case of charged SYK, is it that this coherent state will be like e to the power a charged operator, exponential matrix operators will be exponential of a charged operator? Just to
I think that would be another extra additional class of states for the charged SYK, because these vertex operators are basically just the chargeless operators that exist in the 2D Liouville theory.
you can have charged operators as well, right? E to the power a charged operator in charged SYK. Those kind of coherent states are also accessible for your answer.
They will be accessible in that case, but those are not the ones I'm considering here.
What is R again?
Yeah, I'll introduce that parameter. So it's a parameter which basically it's related to the Neumann boundary conditions on the open string Liouville theory, and it decides whether the states that I'm creating lie on the elliptic orbit or the hyperbolic orbit. So it's like a parameter, it parameterizes the state, the properties of the state.
I'm trying to understand what this correspondence means. So, are you saying that because you have the word parabolic 3 times
Yeah,
for each of them?
yeah.
So, I'm trying to understand, is the statement that hyperbolic coadjoint orbits do not, the states corresponding to those do not eigenstate thermalize?
Yes,
That's correct.
yes.
And this is generically true.
What do you mean? It's true in this case. What do you what exactly do you mean generically? Like I'm not committing to any statement of eigenstate thermalization for any other groups or yeah. Okay.
And do you assume large central charge anywhere for thermalization?
Yes. So that will be the so large central charge of the 2D CFT would be kind of related to the classical parameter, the parameter which is taken to infinity in the classical. Okay. So so now let me start with describing the construction of the two-dimensional Liouville theory. So I'll be studying the Liouville theory on a strip, so that the spatial dimension of the strip goes from 0 to beta by 2. But this beta is not in any way related to the temperature of the two-dimensional theory. Okay, and now since it's a theory defined on an open string, I can impose different boundary conditions on at sigma equals 0 or sigma equals beta by 2, and the conformal symmetry restricts the type of boundary conditions I can impose. If I require that the boundary condition itself be symmetric under conformal transformations, then I can only have Dirichlet boundary condition where the field phi goes to infinity on the boundary, or the Neumann boundary conditions where the derivative of the phi field on the boundary is related by this in this particular form. Okay.
That's your R.
That's my R. Yes, that's the Neumann boundary condition that.
R meaning the 2D, what is that?
It's a family of Neumann. Neumann boundary condition doesn't come as like
Yes.
the usual del phi.
Yes.
I see.
So naively, when I say Neumann boundary condition, immediately I usually think of del sigma phi equals 0. But then, like there's a more general class of boundary conditions which are consistent with the
I say this is the R
conformal.
parameter that he had in the previous.
Yes.
That's what you were saying. I see.
Yes.
Thank you.
Is that like a B field coupling on the verge?
I'm sorry.
Extra R coupling. Usually when you have a B field in the case of a scalar, for example,
Right.
you have a B mu.
No, this is not any bulk coupling. It's just an additional boundary term in the action that I'll have.
Usually when you have a constant B field in the target space,
Yeah.
you put it back, it becomes a boundary term in the verge.
Ah.
So that modifies Neumann boundary condition.
Right. It could be that. I don't know about it. Okay. So right. So and the Hamiltonian of the two-dimensional Liouville theory is given in this particular fashion, where I've included a improvement term to make sure that the trace of the stress tensor is 0. Okay, and the central charge of the theory is, I'll be writing it in terms of another parameter b, which is related to the central charge by this formula, such that large central charge limit is same as b going to 0 limit.
What is the sigma?
This is two derivatives of sigma on the phi field.
Rescaled the phi B or something related to the standard right?
So this I'm
E to the B phi, right?
yes, but that is when the phi is a quantum mechanical field, right? Since I am interested in first writing down the exact quantum mechanical expressions, I will be working with that, like e to the power b phi, and not e to the power phi, where I have already scaled the phi field
But
in
this
the
one
class.
is the scale version.
Uh,
There's no B square outside Hamilton.
oh yes. This one is the scale version. Yeah.
So here V is a function of R. V central charge cares about R.
This R?
Yes.
No.
It's independent.
Yes.
In the previous slide, I was looking at states there. They are leveled by R.
Yes.
And so if you want to take this state to be heavy, what do you have to do to R? Are you going to take R too large or something?
No. So these states are created by starting with some pure state like this, and then acting on it like a order 1 vertex operator. Okay. So these states are, the background states are themselves heavy in that case.
Okay. They are already heavy.
Yes. Okay.
So you should know this, but the improvement term is phi with two derivatives along the sigma then?
Yes.
This is not related to the fact that in Liouville theory, TZZ should have a del z square phi in addition to del z phi whole square.
No, that is already captured in the first terms. That's an additional term. Yes.
Other stuff.
Yes.
That's what I was also thinking. That's the usual improvement.
Yeah.
That's not directly what gives rise to this phi sigma sigma.
Yeah, from what I remembered, that was not the case. Yeah, I needed this term additionally on top of that.
I see this H will not be after going to cylindrical coordinates, whatever L0 plus L0 bar becomes.
No, yes. That would be, yeah, I just forget the details here, but it could be, yeah. But from what I remember, that would just capture this part and not the last term.
I see.
Okay.
Yeah, then you couple that to a little bit of gravity, and that will give you the del Z square phi. That's how it usually happens.
Mhm.
Without that thing.
Yeah. So this is basically, it's not just the so this comes, so this is that additional improvement term that that R phi kind of term that you need to put there.
Yeah.
So R phi is the one that gives you the del Z square phi, because R is like
Box inverse.
Right.
Box of phi. So
Yeah.
R box inverse R is R phi.
Right.
so. But you are saying this is not quite connected to that sort of stuff.
I'll just check this after the talk and
Pranjal, one last question.
Yeah.
Why is phi equal to 0 not a valid condition?
Because under conformal transformations, the phi is shifted, so the boundary condition is not invariant.
E to the phi scales with the factor.
Yes, yes, yes. Okay. So and I'll be like working with the phase space path integral instead of the usual configuration space path integral, because it will turn out to be just easier to work with this. The answers of course don't change. And to impose the boundary conditions, I'll have an additional boundary term of the action, which again contains that R term, which is an R dependent term in the action. Okay, so we
I mean, this is K times phi in suitable units. So there is just from, if I naively thought about the action R box inverse R by going to conformal gauge, I'll get R times phi.
yes,
And then there's a Gibbons-Hawking like term for that, which is probably K times phi.
yes.
Is that what this term is, or it seems to depend on R, so it's not quite that. It depends, but it may be that to get a well-defined variational principle with the Dirichlet, okay, yeah.
With the Neumann boundary condition.
With the Neumann, because that Gibbons-Hawking is usually geared for Dirichlet, and here you have Neumann.
Yeah.
All right, fine.
So I didn't check it with the coupled gravity coupled consistent thing, but I started with the usual action, and if I required that this boundary condition comes from a boundary term in the action, that's how I derived this part of the.
Fair enough, okay.
Yeah. And out of my bias of working on a plane, I will do a exponential map that takes me from the strip to the upper half plane, and I'll be working with the upper half plane. That's completely based on my bias of working with things. So this, when I compute the stress tensor, the holomorphic and the anti-holomorphic part of the stress tensor, then I would require that the flux through the boundary, which after the exponential map lies at the real axis, I require that the flux through that boundary is 0, which is same as saying that the holomorphic and the anti-holomorphic stress tensor are equal on the real line. Okay, and
Really sorry, but you had two disconnected boundaries originally.
Yes.
And then the upper, so how do they map just on the upper half plane? I should know this, but.
it's the
Just
standard.
real line,
Yeah, it's like this. So this boundary goes to the positive real axis, and this guy goes to the negative real
So
axis.
at the origin you have something interesting.
Yes.
Then it's disconnected.
Yes. Okay, and good. So while this vanishing flux condition comes naturally when you're imposing the Neumann boundary conditions, I'll like impose it addition on top of by hand for even digital boundary condition, because of course I don't want any flux coming in or going out through the boundaries of my strip. Okay. Good. So after that, like once I relate the holomorphic and the anti-holomorphic part of the stress tensor on the real line, I can use the doubling trick for that was defined for any boundary CFT by Cardy in his old famous paper, by saying that the stress tensor on the lower half plane is given by the anti-holomorphic part of the stress tensor. And what it does is that it then leaves me with only just the holomorphic part in the theory, and there is no anti-holomorphic part, and the stress tensor itself becomes periodic with a period beta, which like now I'm saying this back in the string language, the original strip language, where the size of the strip was beta by 2, but since I've doubled the whole system, the periodicity of the stress tensor is beta and not beta by 2. Okay. Now I want to look at the classical solutions of this theory, and
So earlier, before you doubled up, you had the whole upper half plane
yes,
and with one boundary. Now with doubling, you have the whole complex plane.
I have the whole complex plane.
And then what did you say about this periodicity with length beta?
So I have the whole complex plane, but the stress the stress tensor in the lower half plane is related to the anti-holomorphic
Yes.
stress tensor in the upper half plane, and now since I'm working with the whole complex plane, the stress tensor when I go around the circle around the origin ones should be same. It should be single valued. So the stress tensor itself becomes from the point of view of the original strip. If I go beta by 2 and then additional, so this lower half plane is an additional beta by 2 added to the original strip, and then this guy is identified with this sigma equals 0. Sigma equals 0 is identified with sigma equals beta in that case. So the stress tensor on the strip becomes, so this is kind of the relation between the closed string and the open string, like open string, closed string is twice of open string kind of thing. So
basically, if you like, the right movers in the fundamental strip are the left movers in the extended.
yes.
What's also R?
What happens to
R that label boundary condition?
right, that will appear again in the solutions, in the classical solutions that I'll be computing next. Okay. So yeah, so now I want to find the solutions for solution of this system, the classical solutions of this system, and I will solve for it assuming that I know what the stress tensor is. So given the stress tensor, I will solve for the solutions that obey the that give you that particular stress tensor. Okay. So so the solutions of these particular equations are basically characterized by the solutions of an auxiliary Hills equations. Okay. So if I look at Hills equation given which is psi double dot minus t psi equals 0, where this t is the same stress tensor that appears here. Okay. Now this has two independent solutions, psi 1 and psi 2. So the solutions of the phi field are related to the independent solutions of this Hills equation by in this particular fashion, where A can be some SL2R matrix. Okay. Now this is a general solution. I have not still imposed the boundary conditions, and imposing boundary conditions is what will like constrain what values the three parameters of this A matrix can take. Okay.
Is it guaranteed that this solves the equations of neutral phi?
It solves the, yes, it's also
This is as you the way you derived it is as a solution of t equals d bar, right?
no. I'm solving these equations as such. The first two equations.
Given it,
Yes.
Given a t and
Given a t, I'm solving for phi for this given t. Okay. And I'm sorry, it's not clear here, but this should be a z bar here. Okay, so because phi depends on both z and z bar.
And when you say that you impose the boundary conditions to find what A is, you'll also need to impose T equals T bar somewhere? Because isn't there a similar constraint coming from getting the T bar equation right?
Yes, so since I'm right, I think yeah. If I use this this identification that z bar equals z, like stress tensor at the anti-holomorphic at the in the lower half plane is related to t bar of z bar, then this and this, both these equations become kind of equivalent.
Oh, I see.
So I mean, it's like if I look at this on the complete complex plane, then that captures both this equation and this equation.
But then you have some condition at the boundary of the upper half plane. I mean, on the
Yes.
on the real.
Yes.
So
Yes.
in that equation, can I just replace psi of z bar by psi of z star, and then it's just I'll be working in a uniform map where t equals to t bar is just true at the horizontal axis.
yeah, I think that's what you mean.
Yes.
Z bar is x
Yes.
star.
Yes.
So, does the boundary condition completely fix the three parameters in there, or you have some hidden there?
The three parameters in A,
Yeah.
it does, yes. The boundary condition completely fixes the parameters in.
So just to clarify, this solution also solves the equation of motion of phi because t is constant.
Yeah. Yes. Yes.
There you have solved it for an unknown function t
Yes.
because t is conserved.
Yes.
But it's a holomorphic function.
So the conservation is same as holomorphicity. Yeah. Okay. So right. So now the solutions of yeah. So now in a general solution of this Hill's equation, the solutions psi 1 and psi 2 obey another like monodromy condition, that when you take z, when you rotate z by a complete circle around the origin, then the solution psi 1 and psi 2 need not come back to themselves. They can come back to themselves up till this monodromy mixing between them, okay, where this M matrix is again the SL2R matrix. Okay. So right. So what happens, the way that the condition that you impose on the boundary between the upper half and the lower half plane translates to the condition that the trace of M gets related to the parameter R over 2. Okay. So this is basically, this is precisely the Neumann boundary condition written after identifying the stress tensor on the upper and lower half plane, and the appropriately, as I said in the previous slide, and it's just, this statement is precisely just that del sigma phi equals r by 2 e to the power phi by 2 on the
This is
boundary.
assuming that it's Neumann and Neumann on both the.
So I'm at present I'm like just talking about one boundary.
Okay, so the upper half plane, so is the boundary of the upper half plane is all Neumann. That's what
Yes. No. What I mean is like I'm considering this boundary, and on this boundary the condition will I'm imposing one particular condition.
Oh.
Okay, and the other condition is Dirichlet. Oh, sorry, I should mention that. So one is Dirichlet.
Yeah.
At sigma equals 0, I have Dirichlet, and sigma equals beta by 2, I have Neumann. That's when this comes out.
So you're doing it boundary by boundary. So so you have to start from the angle 0 and then come back to 2 pi
Yeah.
into, and how about the other one? For the other one, you start from pi and go to 3 pi, or what? I mean, what I mean is that how come it sees only one boundary?
I think if you had Dirichlet, nothing would happen, right?
Yes,
If you had
when you have
always-
Dirichlet, then nothing happens.
So only
So
if
one
you-
is Dirichlet, one is Neumann. So there are both the boundaries.
Okay, I
only
see.
the negative real axis contributes to the monodromy. Positive real axis goes through.
Yes.
Even if you have both Neumann with the same R, nothing will happen. Well, it could be, depends on the.
On the value of R. It depends on.
R and minus R or something, you will come back, right? Yeah, there's some combination. I thought it was just R. R and R. Yeah. Some other things change, but this trace will not. There will be no other solution. Suppose R
Yeah.
is suppose R is 0, then it's the standard one. Then there is no more.
Yeah.
Yes, even if R is not 0, but it's the same R on both boundaries.
So for now, yeah. Yeah.
Because I know that a similar thing happens when you have an open string with a B field with a constant between target fields. There, if you have the same B field value on both boundaries, same electric charges on both boundaries, standard, this monodromy is not present.
Okay. Okay. So basically, what happens?
So the fact that you have Dirichlet also means that phi somehow goes to infinity on the positive real axis.
Yes.
And it is a feature of the solution,
Yes.
which is not clear, right?
So phi going to infinity would be like.
Somehow for real z or something, the
Psi
right
goes
hand
Yes.
side vanishes.
Yes.
Real and positive, yeah. It vanishes. We both independent or whatever the right hand side is when you take psi 1, psi 2, etc. For any A belonging to SL2R has this property
Yes.
in Hill's equation.
Yes. So right. So now the different the value of the monodromy of the solution is what basically characterizes the different orbits. So the elliptic orbit corresponds to when the value of r is between minus square root of 2 and plus square root of 2. And in that case, I define a new parameter which is just equivalent to r, which is this theta parameter, and that parameter is real. Okay. When r is exactly plus minus square root of 2, then that's a parabolic orbit, and the theta is plus minus 1, and for r greater than 2, theta is imaginary, and I am working with the hyperbolic orbit.
Bit confused. The Hill's equation does not have any R in it, right?
The Hill's equation does not have any r in it, but there are different classes of solutions of Hill's equation. That's what I meant here.
Two linearly independent solutions.
Yes, and those independent solutions,
Yeah.
after going after a 2 pi rotation, could either come back to themselves, which would corresponds to a monodromy of 1, okay, which would correspond to the parabolic orbit, but it could also happen that psi 1 goes to so basically psi 1 it goes to rho times psi 1, and psi 2 goes to 1 by rho times psi 2.
So the rho and 1 over rho are determined by what are they determined by?
So this can be either just a phase, so it's like
No, but
coming.
what is the initial specification that leads you to this?
A contains R, right?
A contains
The solution which you've written, A.
No, but
No,
but this
A does not
this
contain
is
R.
statement about psi.
Yes.
This is not even phi. So for that, if I just solve this equation, I don't know what R is. And then I do this monodromy. I take these solutions to this monodromy. What do I find?
I find that there's a parameter which is in that case just trace of monodromy. It gets related to R by like only when I'm talking about the Liouville theory, because
No, but trace of monodromy is what appearing?
trace of monodromy
It
is
depends on the T. Is that the point? So that's
no, it does not depend on T. Like even for a given T, you can have different solutions which are not necessarily periodic.
But how is R entering psi? Like in the first equation you wrote, there is no R. So psi, the solutions to the Hill's equation don't have any information about R, but they do have a certain monodromy, and that determines your R.
So the R, yeah, so the R is basically the monodromy of the solutions.
But then where did that information get in? I'm saying that information should basically come from the boundary term you put in, right? In a boundary term you put a specific parameter.
Yes.
And how did the Hill's equation get that information? That's
No,
what
I think that solution is just the analog of solution of Laplace equation. And then when you impose boundary conditions, you pick up particular solutions of the Laplace equation.
But I thought that the boundary conditions would only fix your A,
No.
right? In the first equation, if psi are like two independent solutions, and then I just fix by boundary conditions would only fix the parameters.
Boundary conditions fix the A. That's what it's.
I see. Okay.
And the parameter A also. So the
Once you put it
yes.
in, it then fix it.
Yes.
Solutions are characterized by only one monodromy, which is related to the fact that you have only one interesting point, that is the origin, that you need to care about only one, sort of like only one branch point. This is the sort of assumption, right? Because if you had more than one branch point in your solution space, then you need to consider more than one monodromy to classify all the solutions.
Right.
And here you have only one monodromy matrix because you have only one interesting point. This is the origin.
Yes.
Or after mapping, this was the joining point. Right?
Yeah, that's what it seemed to be, because these two boundaries are mapped to the positive and negative axis, so the boundary conditions
There
will
are two. One is the origin, one is the
infinity also.
We can have a
Right. When I said one branch point, I meant on the finite.
Yeah.
Because the branch cut is going to infinity means there is a
Yeah.
branch
Oh,
point.
I see, at infinity also you'll have, okay.
They'll have opposite. Monodromy.
Yeah, yeah.
So in this case, there is only one interesting point, because like alternatively, I can think of like a boundary condition changing operator inserted at the origin, and it is the monodromy of that particular operator that I'm measuring here. Like while talking about, I mean, all the in this language, I'm not really saying that, but that's the picture that goes behind the scenes.
So if T were a constant, let's say some
Yes.
special case,
Yes.
then what is this trace M? What is M in that case?
So
That's some
There are two different inputs, right? One is your, if you just go ahead and naively analyze the equation solution of the 5G.
no.
Then there
Just
is
let's
a-
talk about this Hill's equation, psi double prime minus.
This is the analog of the bulk equation solution of 5. And then you have to impose additional boundary conditions, which will fix the solution to some extent.
At what stage does the boundary condition? So so T and T is the independent data, right? That's my input,
yeah.
and then I solve for psi.
Yes.
Okay, and then I plug that in there to solve for phi eventually.
Yes. And even for a given t,
Right.
there are different solutions for this equation.
Yeah, let's take T to be constant. What are
Yes.
the solutions and what is M?
So there will be again three classes of solution, which corresponds to all three monodromies.
Let's say that T is insensitive to what we mean.
Actually, no. That's not how exactly I meant to say. So I can go. So I can talking about it on a plane. I can write t equals theta square, where theta is this parameter, upon 4z square. Okay,
Oh.
that corresponds to vacuum.
T has that.
Yes.
That's what I was asking.
Yes.
Yeah. So, but why is
So is that the 1 point?
Yeah.
Yes.
Why is it of this form? So in particular, the constant thing that I was saying is not allowed, right?
So when the T is not of this form, it's just related by a conformal transformation. Like T is this plus some Schwarzian correction. So if I perform a conformal transformation, I can take it to any non-constant T. It won't change your orbit. A conformal transformation won't take you from one orbit to other.
So you're saying you can always bring it to this form and then read off this theta.
Yes. And like the standard vacuum that we know of is the one where this theta is 1, like corresponding to the parabolic guy.
Maybe another way to see it is, suppose we have some solution psi which satisfies that monodromy mechanism. Then we can use that to obtain T by doing psi double dash by psi. That's how we probably get the theta from it. You can invert the process here. Fix the monodromy for some psi. Assume it's a solution of psi double dash equal to T psi. And then we get T from that.
Yes.
C double dash by psi. Psi double dash by psi. And that will, and then take its 1 point function. Then will be
Right. Yeah. That's how I meant to present it in the when I was saying that like there are different solutions for psi to begin with, and then the T gets fixed. But
So T is not, I mean, this is only the vacuum. T is
this is the vacuum. Yeah.
And then the various classical solutions for phi will represent various excited states.
Yes.
For which T will be different.
Yes. But so this is like the representative guy. So when in terms of the orbit,
I would think that this is only the vacuum.
this is the vacuum of different orbits depending on the value of theta. Like it's like one on a given orbit, it is the stress tensor corresponding to one particular representative.
So, sorry, just to ask you, since I'm so ignorant, these are some coadjoint orbits, something like that. These are orbits on what? On diff S1?
It's orbits on diff S1. So the elliptic and the hyperbolic cases would correspond to diff S1 mod U1, while the parabolic case would correspond to diff S1 mod SL2R.
The orbit in the solution language is just changing n by SL2R adjoint transformation.
Yeah.
Right?
Yes.
It preserves the
Yes.
basic solution.
Yes.
So we have n which fixes the boundary condition for the solution, but we can take some S m S inverse,
Okay, similar.
which still has trace m equal trace S and S inverse equal to that.
Yes.
That will have the same.
I see.
So it's the entire orbit of SL2R, which corresponds to the minus 5.
With that
Thank
in
you,
mind,
thank you.
with that different m, if you were to compute T, it would be different. It would be a different representative.
Yes. So that would correspond to a conformal transformation. Yeah.
The conformal transformation in the Schwarzian piece.
Yes. So of course there will be this times the Jacobian piece plus a Schwarzian piece.
So just to process what Naveen was saying, so if I did a general, I guess, transformation on M, which keeps it within SL2R, I guess just a general similarity transformation,
Yes.
right, which will keep it. Then under that,
The transform rate should also be in SL2R. So I guess the only other ones are where the transformation matrix is also in SL2R.
is in SL2R. Okay, yes. All right, so if I do S, N goes to M, goes to S, M, S inverse, where S is in SL2R, then in general, phi will change. Because,
yes.
you know, there's a transpose,
Yes.
etc., etc. And that entire orbit you get is the orbit you refer to.
Yes.
Okay,
It's
thank you.
parameterized by the R.
Yeah.
Parameterized by R,
But
the trace of M, which is in there. Thank you.
why is it not complete SL2R at the other two things? I mean, why the modded by SL2R is only at root 2? if I do an SL2R on the solution, it doesn't change, remains same?
So it corresponds to that modding thing, like depends on what is the symmetry of the monodromy matrix. So when you are doing S, M, S inverse,
Yeah.
so there will be another class of S which leaves the M invariant even with S in SL2R.
So you're saying that when trace of M is root 2, it has 1 by root 2, it has a special property.
Right.
Usually this trace m equal to 2 is the assured value.
It's just some different scaling. So like okay, that scaling precisely, yeah, I don't remember where that scaling changes. I think it's the different scaling of the fields.
But so your r should be greater than square root 2, I guess, for like
Oh, yeah, right here, yes, that's a typo.
So it's the boundary value is 2 or square root of 2.
Yeah.
Mm.
I mean, in some references, it's also that trace m equal. The one is the cutoff point, like the phase transition point. So, yeah.
What's the minus 2 minus square root 2 is what?
Those are some unstable solutions. Like they won't have. Yeah, the Hilbert space corresponding to those solutions is bottomless. So I'm not considering those cases.
Because t somehow becomes negative.
These, yeah.
Theta squares that.
Wait.
No, but for hyperbolic theta is already IR. Oh yeah.
Right, and
No, he doesn't have what it means to have
R
greater than
smaller.
minus square.
Mm.
He said that some corresponds to unstable solution.
And what about between plus square root of 2 and 2?
Oh, this is square root of 2. That's a typo. Yeah.
So there's another thing that your solutions are actually then parameterized by some arbitrary holomorphic function of z. I mean, arbitrary function of z, right? Or the various other t's will be
Yes.
generated along the orbit.
Yes.
Will be generated by some holomorphic function, some f of z.
Yes.
So, so it's not quite the diff S1 kind of stuff that we are familiar with, in which it's f of t or f of tau, whatever, but it's f of z.
Yes.
Right.
It's not the same. F of z is like t plus sigma. Yeah, but at the end of the day,
I mean, it's a Latcon, you know, if you're
holomorphic conformal transformations will be diff S1, right?
holomorphic conformal transformations
I
will
mean,
be.
z in some sense is the like.
Yeah, so I'm just saying that in terms of some compactification, you know, the natural thing then would be to identify the z itself as my time thing. But you know, what he's going to do, I believe, is a normal comes the time.
Oh.
Yes.
Okay.
Really sorry, can you just go back to the previous transparency, which is what you've solved, what you found are solutions to t of z equal to this, right?
Yes.
But what about just if I had the classical Liouville theory you started with your improvement term and so on, just from the point of view of Liouville theory, you'd be interested in solutions to the equation of motion for the Liouville field coming from there, right?
Right.
What is the relation of those solutions to what you're finding here?
So since this stress tensor is on shell, so these are actually the solutions of the original Liouville theory also.
For any t of z?
Yes, as long as it's holomorphic.
As long
Yes.
as it's holomorphic.
So I mean, the holomorphicity is just like it's all. I've assumed holomorphicity in the way I've written. I'm working with the stress tensors here. Yes.
So people build phase space of Liouville theory out of those classical solutions.
Okay. So now the most general solution finally, like if I finally write down the most general solution, this is uh, this is the general solution of the classical Liouville theory, where the parameter theta appears in the solution, and it basically, so these are some f fields which again can be related to the psi fields that were appearing previously. It's just like one holomorphic field that appears here. Okay. And now, yeah, this I have already said that I can always do a conformal transformation to go to some constant representative, which parameterizes what orbit I am lying on. Basically, the whole class.
The representative would be a special form.
Yes. Yes. So actually, this is the one corresponding to this particular stress tensor.
Where f is how?
Where f is identity, is in f of z is z. Okay.
And if you didn't do that, then the t would be theta square by 4z square times f prime z square plus the Schwarzian
Schwarzian,
derivative
yes,
of capital F.
yes,
Right? That
yes,
would be the
yes.
And I thought until the last transparency that phi was just a function of z, because you had gone to the full complex plane but taken to z. That is wrong, because here now I see z bar, so there must be something wrong in my earlier understanding. I mean, if you just go back once more to the previous, wasn't it true that psi was a function of z, and then
But then
Oh,
there's
psi
There.
z bar.
was
Z bar, yes. You might, I'm sorry, there is a typo here, that's why you got confused. Yeah.
Good,
And
excellent.
also the stress tensor is holomorphic, but the phi field is not.
It's yeah.
Only the currents are made to holomorphic fields on the double plane, but not the fundamental view.
And it incorporates this boundary condition that T bar of Z bar is T of Z star.
Yes.
When was this done? 0608, as recent as this.
Yeah.
Same here. Good, thank you.
Actually, I think mathematicians have known this for a bit longer, because, yeah,
Without understanding.
okay. So now, now I'll go back to the path integral, because now I want to quantize around these classical solutions of the Liouville theory, and I would do a transformation that, so I wrote down my path integral in the phase space language. So I do it's not a canonical transformation, but a coordinate transformation in the phase space, such that I go from some phi and pi fields to these capital F fields, okay, which characterize the classical solutions of the Liouville theory. So after performing this rather complicated looking transformation in the original path integral, what I find is that the action for the original Liouville action becomes the Schwarzian action in 2 dimensions right now. Okay, so it has this Schwarzian piece, and there's an additional piece which is the pi phi dot piece. Okay, but now if I take the classical limit, I know, like this we know very well, that when we take the classical limit, then the pi phi dot terms, classical limit is like this b, which was related to central charge, this going to 0, so that this coefficient is infinity, then the pi phi dot term drops out of the phase space path integral, because the solutions on which you condense is the one which are independent of the time direction. Okay, and So therefore, taking this classical limit, after taking the classical limit, what you are left with is precisely the Schwarzian action. Okay.
Is this supposed, I mean, for a non-classical mechanics problem, the phi dot, I mean, take a harmonic oscillator or something, that won't drop out in the classical limit, right? Am I right? Am I misunderstanding? I mean, because in a sense, if pi is phi dot, that's just phi dot square. I mean, why should it? Am I missing something?
If so, I'm okay. One way to look at it is like if I scale the time coordinate here itself with 1 over b. Okay, then the only the term which is the pi phi dot term has one time derivative here and this dt. So the scaling cancels here, so it still has this 1 over b square term here. Okay, but the 1 over b square term, so I am scaling the time with 1 over b square, vanishes from the remaining Hamiltonian part of the action. Okay, so the dominant in the b going to 0 limit, the dominant part is just this pi phi dot term, and the variation of the pi phi dot term gives you the solutions corresponding to pi dot equals 0 and phi dot equals 0.
Okay, just to make sure, now I'm a little confused. You've changed, so first you change variables from phi and pi phi to f.
Yes,
And what did you say? Is it a canonical or no?
it's not a canonical.
Okay, but it's a change of variables. And now you get phi dot of f, and how do I understand that? I mean, presumably there's some definition of pi of f,
Yes,
which you haven't told us.
this is the definition of pi of f.
Oh, it's not pi of phi, it's pi of f. Just to
It's pi phi is in.
Oh, that's what you mean by this.
Yes.
Okay,
Pi phi expressed.
okay,
Yes.
I understand. And the phi dot is still to be understood, okay, and dot is a time derivative.
Dot is the time derivative.
Now I understand. Yes. Go ahead. Okay.
This was already present in the Liouville action earlier, right? The one that you wrote.
Right, it was, yes.
But there were other terms which you say drop out in b going to 0 limit. You are left with.
No, this is till now it's all exact.
Oh, the remaining terms are in terms
So,
of f.
yes, or the Hamiltonian term in the original part, the action that I wrote down is this, and this is still the pi phi dot term.
I mean, what I would have naively thought is in the classical limit, in some sense, you condense onto just the classical solutions to the Liouville equation of motion. That's what I would have thought,
Mhm.
right? Is that what's finally going to happen here?
Yeah,
Because those are all parameterized by f. So you're essentially writing down an action for f. Is that correct?
that's, yes, that's,
Action also simplifies.
yeah.
Any f satisfies the, if I understood, if I took your first equation, e to the minus phi over, any f satisfies the
So
Liouville.
why is there an action?
No,
No, I think any f, this dot, are you giving some, is it like collective coordinates and so on, in which now all f of z's, the holomorphic guys, are solutions. Now you're adding some little bit of z bar dependence to this, so that you are picking up some action.
no, I'm not doing that exactly.
You're not doing
So first I,
But what's dot then? What is this dot?
this dot,
Yeah.
this is time derivative of the phi.
Oh, sorry, where is time?
Time is like z minus z bar or z plus z minus z bar.
Z minus z bar. So clearly you are then adding to f of z some additional dependence on something. That's right.
No, I don't see, why do you say so?
Exactly the same question as Sandeep and I think Abhijit are asking. It's like a soliton solution
Mm-hmm.
in which if you take the soliton parameters, whatever it is, for all parameters, these are solutions. So as a result, you will not pick up any action. But then, if you make the solitone parameters functions of t, x, and whatnot, then you will pick up stuff like ion kinetic energy.
No, but he's going to drop that out anyway.
Actually, f of z, isn't it just alpha plus beta z plus gamma z square for the solutions? And the remaining ones are the Virasoro problems, right, which have some cost in the Schwarzian.
No, but this was
It
not
was
a
the
cost,
solution.
right? You had a solution.
But the solution had 3 real parameters in that game.
Yes.
So an arbitrary f cannot be the solution.
It
You
is.
have an
That is
No,
the solution.
that is the solution with an arbitrary f.
Those three parameters are just one parameter now. That's theta.
That's the theta.
Yeah.
So the parameter count is also
No, so I'm also looking at like the different solutions on the orbit. That's how f is coming back.
So when you say orbit, do you mean SL2 orbit or Virasoro orbit?
Virasoro orbit. So, so the conformal transformations on top. When I was discussing 2 slides back, I was discussing only the. Huh?
This was SL2R, the elliptic, parabolic, hyperbolic stuff that we did now.
Right. But then the full, like I can apply any general conformal transformation to generate a whole orbit, like of solutions.
Isn't this related to your S matrix you were mentioning? That's what is generating the orbit, right? So you will get bigger set of solutions.
Yeah.
I was imagining S to be just in SL2R, it's the global part of that Virasoro. But apparently, even if you do the other higher if you use higher generators in the Virasoro to generate new candidate solutions, they still satisfy.
Because those corresponds to this. So these solutions are corresponding to the stress. This just the constant representative of stress tensor. So once you apply the conformal transformations.
The extra terms will arise only if the Schwarzian is non-zero for those
Yes. Yes.
And those are the
Yes.
few bonds.
Yes.
I see. Because it's a bigger, I see, answer.
Sorry, what? So if only for the singularity transformation, I mean, base living in SL2R, do you generate these new solutions? Otherwise, not.
We'll generate only the 3 parameters of orbit, I guess.
Yeah.
But if we want more solutions, I guess we have to go for the other Virasoro transformations.
Well, those would not give you solutions, yes.
No,
Those would give you
that was my question, but apparently it will give
They will give the solutions. Yes.
all that is required for this to satisfy the Liouville equations of motion is that T is holomorphic and
Yeah.
that is preserved by all these Virasoro transformations.
Yeah.
So I guess I take that.
But then how are you getting action for
Yeah.
Yeah, that question.
No, but the general F transformation is not a symmetry transformation, right? The symmetry transformation was just the SL2R or a subset of it. It's either U1 or SL2R is the symmetry transformation. A more general transformation does cost something. That's why you have an action associated with it.
Wait, then there should not be solutions of the equations of motion.
Can I just ask one small thing? It is one thing to ask what is the on-shell value of the action, but just that action you wrote down in phase space with the theta
Yes.
which you are dropping. If I vary it to get a solution, do I get back all the original solutions or not? I mean, that's what we are asking.
Yeah, you will get SL2R, right? Because if he drops this first term, then just a Schwarzian. And that is SL2R, right?
The only solutions are. You're right. You're right. You're right. You're right. You're right. Yeah. Okay, sorry. At least for theta equal to 1.
Yes.
I don't know if that's a way out.
I'm sorry, can you say again what you said?
I mean, if you, let's drop this first term that you are
Yes.
dropped. Now the remaining action, if
Mm.
you solve, if you find the solutions for F, you would just get the SL2R.
On shell, yes.
Yeah,
On shell, yes.
So does that means that other transformations cost,
Yes.
they are not
Yes.
solutions?
Yes.
Of this, that should also mean that the f image of phi was not a solution of the previous guy, right? Because this is just a action for your f image of phi of the previous Liouville action, right?
Right.
So these two statements don't seem to be consistent.
Maybe f is not a symmetry of the thing. So these are at every value of f, you have a solution to the equation of motion, but they have different energies.
Yes.
They have different energies, energies or whatever. They have different actions. Yeah.
So, in other words, is the statement that what is boxed above is a way to try and parameterize functional dependence of phi, but it's not solutions? That is
Actually, that's the right thing.
That is
Yes.
the correct
That's the
statement.
right thing. Yes.
Okay.
But you're saying that the first line is not a solution to the integral?
It's
general,
in
for
general.
general
Yeah.
For a given f, any f, it's not a solution.
No, I think it's a solution.
But
f
for a
is
different
symmetry.
given stress tensor and like for different f's, you will get different stress tensors.
Right.
Yeah.
That's all.
But didn't you tell us that for any t of z, if you solve for phi in the way you described, you would be solving the Liouville equation of motion?
Yeah.
So then, just from the point of view of solutions to the Liouville equation of motion, any f would be a solution.
Yeah, I think there's a little probably we have to distinguish between solutions of equations of motion versus things which are related by symmetries. See, all these stress tensors, they are different. They have a new term corresponding to capital F being non-identity. So therefore, clearly, although all of them are solutions of equation of motion, they have different
They have
energies.
different energies.
Just like free particles can have x equal to v times t, but they are all different solutions.
This is kind of also true for all the Brownhill geometries.
Yeah.
All the Brownhill geometries are solutions, but they have different actions.
Yeah. They have different stress tensors. They're all.
Well, this if you have degenerate saddle point, they should not have the same.
So these are not related by symmetries.
Yeah.
These are really solution generating techniques, but the solution generating techniques are not symmetries here. So all these points in this solution orbit of f, okay, they are not symmetry orbits.
So this S Liouville which you have written down, that's the value of the action on any one of these solutions.
That's right.
Right.
When B going to zero limit, you're going to isolate some subset of those solutions.
Yes.
Which are these constant ones.
Actually, I wouldn't restrict myself to constant, guys. I'll keep the path integral. I'll take the b going to zero limit, but I won't condense this because I'll take b going to zero limit. So I get a one-dimensional action, and when I get a b going to zero limit, I will simultaneously take a going to zero.
Keep some modes.
And I keep the ratio of a over b square fixed.
But maybe if we just do the B going to zero limit, out of these infinite class of solutions, we will just get 3 parameter solution.
Yes, yes.
So it's some analog of collective quantization, the quantization of the collective modes, that's what we should understand. The f of z is like the solitron centered anywhere, and then he's quantizing the center of mass of the solitron. Is it the analog of that? Do you think?
That's what I thought first, but it might simply be the fact that different f's, although they are all solutions of equation of motion, okay, they have different energies. That you can have.
That you can have.
So just that. That's
Even
this,
with a
this,
continuous space of solutions, you can
they can be parameters by different things. They're just like free particles can have x equal to vt as a solution, but different v's are all different. I mean, you pick up some on-shell action for this half mv square, which are all different. They're all solutions, but they're not solutions related by any symmetry.
What I'm trying to just understand is what's the further manipulation being done here? There is showed that this is a complete set of solutions for Liouville equation motion parameterized by f, etc. And then you're still in the classical limit. What's the additional here? What's going on? I haven't quite understood this. That is, are you going to get
In the
further
dropping
restriction?
of
Yeah.
the pi
In the
finally.
end, okay, let me ask this. In the end, you're going to get some restrictions on f of z.
No.
Okay.
So I get a one-dimensional a path integral for a one-dimensional theory. Okay, and now I think I
and that degree of freedom which you get, by one dimensional you mean with the harmonic oscillator, what does one dimension mean? The target space is one dimensional?
no, the one-dimensional is in instead of being on a strip, like one of the dimensions of the strip becomes irrelevant, the time direction.
Okay, so it's literally like the harmonic oscillator which depends on time, instead of that things depend on sigma. You have some variables depending on one dimension in that sense.
Yes.
And this variable which appears is just f of z or but now as a function of sigma or what? Or some how is little f related to
Capital, oh, I'm sorry, I didn't write that. So capital F of Z restricted since it does not depend on time anymore. So there is only sigma here. Okay, so this is e to the power 2 pi I small f of sigma over beta.
We go back to that variable change that you did from the pi.
Yeah.
So that is not a complete variable change, right, in the phase space. You have restricted phi and pi to the solutions of the Liouville equations, and then you have done the variable change to it.
Yes.
So we have already restricted the range of integration in the path integral to solutions.
So I'm kind of that's what you usually do when you're quantizing around those solutions.
Right.
So that's what I'm doing.
But you're not even considering fluctuations about that solution yet. You're still in the space of solutions, and you're still looking at the action in that space of solutions. Right? When you're doing a different kind of classical limit there. So when you're quantized around a solution, like Gautam was saying, you fix a classical solution and then you look at fluctuations.
Yes.
But this is not the action for those fluctuations.
No.
Understand that?
No.
There are further pieces which are ignored.
I think that the thing that got dropped is the fluctuation.
No, that's
But it's
I mean-
just the action evaluated on the solution, right? That's what it is. In the b going to 0 limit, that's the problem. But if you don't take b going to 0, that's still present.
Yeah, so I'm just saying that the fluctuations, I mean, it's like really doing a saddle point approximation in which you have a lot of saddles and I'm summing over all the saddles. It
Right, but
turns
there's
out,
you're not included the quadratic piece of the fluctuation on top of the value of the action.
Which would be anti-holomorphic, right? Which would be like
Which would have some z bar.
Yeah.
So that's not this phi dot. That's not captured by the phi dot.
yeah, that's right. Because this is the complete action at finite b.
Yeah, what is the dot? This dot is what? I suspect that it is the other.
Yeah, it's time derivative. So
It
it
is
will
so
have z
it
bar
will
plus
have both the
some-
z and z bar
That's
derivative.
right. I think so. I think the solution, this f of z guys, they are all, for all holomorphic fellows, these are solutions.
Yes.
Now, if I do the way I do collective coordinates, I put in the additional dependence on the additional coordinates, like z bar here.
Mm-hmm.
And dot could be the z bar derivative, is it? Or
Dot is just z del z plus z bar del z bar.
Yeah.
But here the point is phi, even if it depends on f and f of z and f of z bar, when you compute the stress tensor for that, that is still holomorphic. Whereas the offshell guys would have a stress tensor which also depends on z bar. These will still give a holomorphic stress.
Even if f of z depends only on z, say does not depend on z bar, still you have a non-zero action. So which says that arbitrary f of z is not a symmetry.
Yeah, this is what is bugging me.
it's not a symmetry, it's a solution generating technique.
No, but it's not even a solution, right? I mean, that is, what's bothering me is if I drop the first term, you get the Schwarzian action, and now ask for something which extremizes the Schwarzian action. I won't get a general function of z as a solution to So that's what is bothering me. I mean, just to be very precise, if I take theta equal to 1, last term also drops out.
Yeah.
Now we have Schwarzian. Now if you vary, if you extremize the Schwarzian, a general function of Z is not a solution to that.
Yes, only this SL to Z.
Yeah, is a solution to that.
So that will say only those SL to Z kind of FZ are the legal
Hi.
solutions of the case.
So that's what is bothering me.
Oh.
That's what I'm not understanding. Yeah, okay, Rishi, yes, his mind does that.
Yeah, maybe,
Yeah, today we have this
Oh,
cosmology.
sorry.
Starting from
I shouldn't.
Cosmologists, they seem very worried about every 5 minutes. They should have a billion-year time scale. But you guys can continue like this. Very up to you.
but I guess we have to vacate the room.
Yeah,
Yeah.
right now we'll have to.
So is there any point in saying that you can go to the summary page?
See, till now I have just summary page I have already given, and till now I didn't even go to the
That's a pity.
calculation in Schwarzian theory.
But you the outline.
Yeah, I can actually outline the remaining things in.
The other thing is, if you're here for some more time, we can have another talk.
He is
Uh,
leaving tomorrow evening.
Oh, okay.
Yeah.
That was evening, sorry, outline.
But I can come back on next Wednesday.
Do that then.
Okay.
Right, and that may make more sense, because otherwise.
Would tomorrow morning be okay?
Tomorrow morning is also fine.
It's at 1.
Tomorrow morning is fine with me.